Hey, it's time to break the box. So open up your box and take all the stuff out of it. If you want, you don't have to do this part. I'm going to break my box and I'm going to make a clipboard for interviewing Dr. Daniel Fried. He's going to be telling us about how he uses computers to model both small and large molecules. So I'm going to take this box and I'm going to cut it up and make a clipboard. Let's get started. Okay, so I have cut my box up and you can see this piece here can be the backing, and I have a couple of different choices for how to hold a piece of paper on for the clip part. So I cut a couple of different pieces and I'm just going to play and see which one of these works the best. Okay, so one way I did this was just to cut the sides off, one of these sides, and just bend it, and it makes a nice little flap there, and then put a rubber band on there, and I can easily stick a piece of paper underneath there for my clipboard, and voila, I have a clipboard and now I can write notes. I could also have used this one to make a flap. That might have worked also, folding it down to make a bigger flap, or I could have used this one to make a flap, but I think this one works just great. So now I have a clipboard. Hi, so today we're going to talk to Dr. Daniel Fried. Dr. Fried is a biochemist and owns Biochemistry Literacy for Kids, which is an online program that helps kids starting in first grade use computers to model small and big molecules. So welcome, Dr. Fried.
Hi, thanks for having me.
Yeah. So before we jump in and talk about computer modeling, tell us a little bit about yourself. Why did you decide to become a biochemist? And what inspired you to launch your own company, Biochemistry Literacy for Kids?
Yeah, sure. So when I was getting interested in biochemistry, it was actually when I was still a music major. So I was at Temple in the music school, and I had always liked science, but I started to have some friends who were pre-med, and I started to look, I was kind of peeking their textbooks, and I started to really wonder if I should be doing that instead. And one day I actually saw a poster, I think it was in front of the biology department, that showed one of these amazing rainbow ribbon diagrams of a, I guess, I didn't know what it was at the time, but it was a protein. And I thought, oh no, I really want to know what that thing is. Like, what is that thing? So I ended up changing majors. I went back to New York, where I finished my BS in biochemistry from Binghamton. And then I was lucky enough to get a PhD from Yale. And during that time, I was working in a protein folding lab. So I ended up doing protein work. And as I was getting into it, I started to think, this is not that hard in the fundamental way. There shouldn't be this 20-year gap between, when a kid enters school and when they're allowed to study these topics, because these are foundational things. Like, what are we made out of? How do our cells work? How do chemical reactions in our cells work? So why is this big delay? Why is biochemistry this elite subject where you have to be at Yale doing your PhD to learn anything about it? So at the end of the PhD, I started to convene these experimental classes. And surprisingly, I would put ads actually on Craigslist. Please send your kid to an experimental science teaching program at Yale. It'll be fine. And the kids really, parents dropped them off, and I was able to do these piloting programs where I was experimenting with modeling and showing kids these different topics that they weren't getting. And I really thought that, this is really working. The kids really want to know this stuff. So after my postdoc, I became a professor, and I started to use that as leverage to, really get into some schools and really see if I could get this to work. And it just, everything I ever tried was working. I was able to do any kind of high level content. The kids just were desperate to know it. And it was up to me to figure out like how to package it in a way that they could learn it really quickly. One thing, when you're working with schools, you have to kind of do everything pretty quick because they have limited time. So that's what happened. And it basically became this idea of like, let's bring it onto the internet. Let's create an online program so that schools can access these materials that I was developing. And then kind of by chance, homeschoolers started to develop, started to access and ask for it also. So now it's this big homeschool program that is getting some traction. And it's really wonderful working with kids all over the world now, and seeing that idea that I had so long ago, just a kind of like a test idea, like just see if this would work, a pilot. And now we have kids all over the place doing it. So it's just super exciting, and it's also a challenge for me to figure out like, oh, what's the next topic I want to do? Like, I just learned something. How could I make kids appreciate this? So it's just been really intellectually amazing to be able to just do this freely. So that's why I have the company, because it's a way for me to just actualize this crazy idea that's turned out to be not so crazy, because kids actually, are doing so well with it.
Yeah, that's exciting, Dr. Fried. I mean, it's so exciting that you could go from, interested in music all the way to getting your doctorate in biochemistry, and now owning your own company, teaching kids all the wonderful things about, computer modeling. So let's dive in and tell me a little bit about specifically how computer modeling programs help kids understand molecules. So this unit that we just did was on molecules, and the kids, we all made little models with marshmallows and toothpicks, and getting kids to understand how modeling helps us understand how molecules work. So why don't you show us a little bit about your computer modeling of maybe small and big molecules, and tell us a little bit about how it helps us understand how molecules work.
Sure. Let me show you something big first, because that's actually because I have one up on my computer already.
Yeah.
And also because that's the way that I like to reach the kids. I like to show them, look at these crazy big things. Don't you want to know more about that? So I will show you one of my go-to structures. This is the green fluorescent protein. And this is the deluxe version. I've kind of worked on this for a few hours to show a lot more than is typically kind of shown in the structure. But what we can see here is a lot of atoms. We can see these ribbons, which are this cartoon representation of the overall protein structure. So using modeling, we just see, we see the molecule in all of its glory at the highest resolution possible, at this atomic level. So that's why I'm interested in showing modeling. I have to actually, I'm going to show you one, because it's actually not ready, to be honest, but I'm going to show you one other thing. This is a completely interactive software. By the way, it's also free. So you can bring up or create a structure and then modify it and show whatever you want. So what I'm actually going to do, because I noticed that this particular one is not showing any hydrogens, and I want to show you this hydrogen bonding concept. So I'm actually going to show them using a little coding here. And they're there. So there are my hydrogens. I added all the hydrogens. Now there's hydrogens all over the molecule. Okay. It's a crazy mess. Okay. I'm going to try to change it a little bit. I'm also going to show you the double bonds where they're needed. There we go. Double bonds. All right. That's a little bit better now. So what I'm going to show you here is what's holding this crazy thing together. Now there's a lot to look at, and I could teach this to you in 12 sessions, but just trust me, there's a lot going on. And if we look, I'm going to show you one small aspect of it. If we zoom up here, you're seeing these kind of dashed bonds, which people may not have known that there's these. What are these? People may know about covalent bonds and ionic bonds, but these dashed bonds, what are these things? These are the hydrogen bonds, and these are so important in biology, because we are held together by hydrogen bonds. DNA and RNA are held together by hydrogen bonds. That's very famous, but also proteins, and proteins kind of do everything that's important in a cell. So it's important to know about hydrogen bonds. So what these are is, this is a connection between lone pair electron, which is on this oxygen right here. I can kind of maybe try to show you. I'll just highlight this oxygen. I'm going to highlight right here. I'm going to show the sphere. So that's the oxygen. And right across the way, there's a white atom, which is the hydrogen. Now that's a special kind of polar interaction. There's an attraction because of dissimilar charges. The oxygen has a lot of negative electrons. The proton here, the hydrogen is more positive. So that's what causes this connection. And you can see there's a lot of connections, right? The whole thing that's really the building block of the whole thing, right? The whole thing has this structure because of hydrogen bonds. So why not learn about that?
Yeah.
This is one of the first things I teach the kids. Yeah, go ahead.
So one of the things is like, immediately you can see that the ionic and covalent bonds are like sticks, right? But these hydrogen bonds aren't like sticks. They're more like just making the molecules a little sticky, right? They're like maybe even, like little magnets when you put them together. They just sort of attract each other.
Yeah, exactly. So what I'll do is I'll undo this and I'll show you how the computer modeling connects to physical models. So I use these physical models. These are actually water molecules, something a little bit more simple than that giant protein. But they're also held together by the same force. So I showed you before that those oxygens had those electron pairs. I mentioned that a minute ago, if you remember. Those have some negative aspect to them, and then the hydrogens on another water molecule have sort of a positive aspect to them. So I use these this custom kit that I use with my program so that we can actually model this kind of connection. And that's actually one of the most important parts of studying water molecules is they can hydrogen bond, and they can also unhydrogen bond, which is why water is water and why water is not ice. If you have permanent hydrogen bonds, you have ice. And if you have fleeting hydrogen bonds, that's a liquid phase. So that exact concept that we may or may not be familiar with in water is at play inside proteins too, and DNA and everything else. So there's that all important hydrogen bond. And so that's one of the, why wouldn't a kid want to learn more after they heard me say that? You know what I mean? So
so the modeling helps us visualize, right? Models are important because, we might think, okay, this is what it looks like. But when we put it together in a model, we can start to see things in 3D if you're doing a 3D model. But what's nice about your program is that you can rotate those molecules, and you can actually, even though it's on a flat computer screen, right, you are seeing the molecule in 3D. And the lesson that we did was about how molecules follow rules.
Yeah.
And so I built a little airplane following the rules, and then we built a little airplane not following the rules. And there's a huge difference between whether or not one airplane can function and one cannot, function. So yes, being able to understand how models also show us how these, that molecule is very well organized, right? It's following these rules about, how it's put together. And hydrogen bonding is one of those elements of atoms that follow a rule and put molecules in certain orientations so they function in certain ways, like the ice and the liquid water, right?
Yeah, and it's totally true. There are very, very specific rules even about how those big structures fold together. So actually I have here I'm trying to show it to you. I have here a physical version, a physical version of what I just showed you here. So this is the same thing. And you can see that there is this, repeating pattern. And one thing that is important to do if you're a scientist is you're always looking for those patterns, right? Because those patterns are the window that we have into like the mind of nature, right? Like how does nature structure itself? So so that's what is going on here. And there is a certain pattern. It's called they call it I to J is the specific pattern here. Basically, this amino acid here is I, and this one's J, and you've got the hydrogen bonds connecting them together. So there is a way to encode that patterning. So yeah, chemistry is all about patterns. And once you see those patterns, everything kind of like opens to you, the door opens, and yeah.
Well, that's fantastic, Dr. Fried. That's very informative about how computers, help us understand how molecules work. The last question I have for you is, what advice would you give our Raditas students if they wanted to pursue a degree in biochemistry or even learn more about your program? Tell us a little bit more about how they can get in touch with you or your Biochemistry Literacy for Kids program.
Yeah, oh, sure, why not? So I'll bring up the website. I can just show it to you really quick. It's a really cool website because people send in all the photos of their kids doing the models.
Yes, it's great.
So it's really cool here. So here's the program. It's called Biochemistry Literacy. If you just type in Google, if you just Google like kids biochemistry or anything like that, you can see all the things. There's a sample lesson actually, where you can hear me talk for an hour about everything. And you can also see the lessons. So the lessons are really cool. We have about 25 lessons or so at this point. on all kinds of things. And it's a great extension if you've already gotten like a start in chemistry, you want to learn about, protein folding and some of the things I talked about there. So that is the website. So the advice that I'd have if people want to, well, I think everyone should learn this kind of stuff, not just if you're going to be a scientist, because as we've seen, like, biochemistry is important. Sometimes things go wrong and biochemists can help fix those problems or try to fix them. So they are an important member of society. So it's good to, be able to know what they're doing, even if you are not one. And I'm not a practicing biochemist at this point. I'm not working in labs developing vaccines or something, but I'm trying to, educate people so that they can, first of all, appreciate the practical aspects, but also appreciate the wonder of nature, because this is this is a world that's closed to most people. They don't know this exists. And when they start to see that this is what we're made out of, these giant, macromolecules, it's amazing. And people want to know more about it. The advice that I'd have is, if you want to actually be a biochemist, you have to be good at science. And for me, it was unfortunate, but I had to be good at math, which I wasn't very good at math. I was not a star student or anything like that. I wasn't at the top of the class. It was hard for me to get through some of these courses. So don't give up. That would be a good piece of advice. If you feel like you aren't, the very top person, don't let it discourage you, because the one advantage that determined people have is that they persist and they last for a long time. Sometimes the people who are, so impressive and so really good and competitive in a class, they may not be around 2 or 3 or 4 years later, but you're still around and you're still working at it. And just how long you can be stubborn about something, how long you can be determined to achieve your goal, that's an advantage. And I coming from music also, I saw that same thing. There were kids that, when I was in music school and in high school, they weren't, the top kid in the state or something, but because they didn't quit, they stayed around, and now they are the best, and you have time on your side. So that's one, actual, piece of advice that you could actually implement, is just everyone says don't give up, but it's more than that. It's don't give up, and you have to last for a long time. If you don't give up for a long time, you will possibly succeed. That's my advice.
Yeah. And I think it helps to stay interested in it. And that's what we're trying to do with Raditas, right? Is if you're asking and answering your own questions and pursuing your own interests, then you're likely to stay with it, even if initially it's difficult, right? Even if initially you don't really understand it very well, or maybe you don't do very well in courses. Over time, you stick with it, you start to learn it, you start to understand it. It becomes more and more and more interesting the more you learn.
Yeah, and that's true. Like, everything's difficult. When I try to learn a new subject to make a course for it, or a lesson, it's hard for me. And like, I don't understand it and I'm super confused. So that's another thing. We're in our own minds, and we know when we're confused, and we know when we feel like we're failing, but you don't know what other people feel. And you have to realize that, like, it's normal. It's normal to be, nervous, or, you're not sure that you're going to be able to do it. That's just part of it. And it's actually good, because that means you're doing something new and you're pushing yourself to do something that you didn't do before. So it's totally fine to feel that way.
Yeah, well, great. Well, Dr. Fried, thank you so much for joining us today. It was really exciting to hear about big macromolecules and how hydrogen bonding works, and more about models. And I appreciate that you joined us. So thanks.
Thanks so much for having me.
Yeah, you're welcome.
Well, thanks for joining me and playing with some marshmallows and toothpicks, making marshmallow molecules. And join me next time. So we're going to look at how chemical reactions happen when molecules meet. Thanks.